tutorials. Okay, in the tutorials, if you go to this particular basic Laplace, if you go to this basic folder, and there you can see Laplacian foam. Okay, Laplacian foam. So here you can look at the flange problem. Okay, you have this flange problem. So we'll try to look into that particular flange problem. Okay, now if you want, you can see, you can remove the all clean, all run, and flange. This particular, all this files you can just remove. Okay, you can remove this, and then you can, we'll try to open the block mesh dict file, and we'll try to solve this. Okay, we'll open the block mesh dict, and we'll try to edit what is there. Just we'll open it in the terminal. It's already the terminal is open. Okay, we'll go to this CD, Dropbox, or from here itself will open. Okay, open this. Okay, I opened this particular folder. We have to go to the, where exactly I told that you have 3 folders. One is the 0 folder where all the initial and boundary conditions are there, and you have your system folder, you have a constant folder. So I'll go to the system folder. Okay, I'll go to CD, system. Okay, in the system folder, I'll just gedit. Okay, gedit space block mesh. M should be capital, D should be capital, DICT. Okay, I opened this particular folder. Very good. Control dict block mesh dict, it is not there. I think you have to copy. It's an empty folder and copy from some other place. Copy this block mesh dict file. Okay, I have this block mesh dict file. I'm trying to open this. Okay, so now if you look at this particular thing, whatever the first set of lines, so what you see, those are called as maybe your header files or whatever it may be. And whatever this particular double thing is there, that is comment lines. Okay, here. If you look at the older files and all, actually older versions of OpenFoam, instead of this convert to meters, they used to call it as scale, that is multiplying. So what the meaning of it means? The meaning is actually, if you try to put this particular 0.01 or 0.1, these vertices points will be multiplied by this number. Okay, suppose if this is 20 centimeters, this 20 centimeters get converted to meters. That's the meaning of it. So 20 into 0.01. Okay. Now what is this vertices actually? I told that this is nothing but the vertices. This is 1. Okay, let me call it as this is vertices 1. This is vertices 2. So I can just go here and can just put a double hash, and just if you want to understand what are these vertices. So this is vertices 1, 2, 3, 4, 5, 6, 7. So maybe if you go to the last one, actually, you can double this thing and you see vertices 8. You can name literally. So this will help you. Say for example, if I try to put a box and all, maybe the behind one I can start with, sorry, what? I have to start with 0. What is 0, 1, 2 till 7. So there are 8 vertices. I can name all the vertices. So what are the dimensions? So maybe in the previous class I told that 0, 0, 1. Then to the right hand side in the x direction it is 20 centimeters. Then y is 0, z is 0. Then I'll move in the y direction. That means something like this. I open the Word file. So x direction, y direction, and z direction. That's what I'm going to do. Let me show you. Opening 1 minute. Yeah. So that means let's try to This is what I have. Okay, that means in the x direction, if I take this as, okay, if this is my this thing, this is my 0, if it is a box or something like that. So 0, and here it is 20, here it is 20. Okay, that is this. For example, if I call this as some kind of a plate, this is a one-dimensional 1D case, some kind of a, maybe we can go with either transient problem or a steady flow problem, doesn't matter. So what I'm going to take, I'm going to take this particular thing. So this is of 0 to 20 centimeter length. Okay, and I'm going to heat it. So if I do a conduction problem, I'm going to heat it. So this will become your hot surface. Okay, this will be your hot surface. Hot surface, and this will be my cold surface. Okay, this will be my cold surface. So what I'm going to do, so heat is flowing from one phase, so from one side to other side. So the simple equation what we have is a Laplace equation. Okay, Laplace equation, dt by co. You have that particular thing. I can use that Laplace equation for heat transfer. So minus Ka into dt by d tau or dt by dx. That particular formula I'm going to use, and I can tell it actually. Okay, now if you look at this particular thing, I'm going to so other side. So this is 0.00. Then this will be 0, 20. 20, 0, 0. Then if I move in the upward direction, so this will be 1. Okay, this is the 1. 0, that is 0 vertices. What is this number 1? Then what is this number 2 and what is number 3? So this will be 20, 1, 0. Okay, then I can come back 0, 1, 0. Okay, that is in the back phase. So then if it is a maybe 3-dimensional kind of a thing, that is, I can have a similar kind of a thing. So it will be something like, okay, I can have something like this. So you can connect from this point to this point. Okay, and connect from this point to this point. And connect from this point to this point, and behind that is there. Okay, that means this becomes some kind of a duct, this thing. So you have 4 faces behind and 4 faces in the front. So if I call this as 0, 1, 2, 3 behind, then I can call 4, 5, 6, 7 in the front. So I'm going to then in between I have the flow here. I have flow, so this is the hot surface, this is the cold surface. So that's what I'm trying to do in the block mesh file. So I have this files 0.00, 20, 0, 0, 20, 1, 0, 0, 1, 0. Then 0, 0, 1, 20, 0, 1, 20, 1, 1 and 0, 1, 1. So all the vertices are defined. Okay, now I have to define the what we call it as maybe mesh actually. I can define the mesh. So it is 0, 1, 2, 3 behind. I told that you can't overlap. See, when I'm trying to define any surface, so I should define the face first, then exactly opposite face first. So it should be something like a mirror. So 0, 1, 2, 3, 4, 5, 6, 7. That's how you should be able to define the faces. So that's what we have done here. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. Then here, when it comes to spacing, so you can keep whatever it say. For example, instead of 100, so let me go with some 300 or 400. Okay, and here I can go with simple, maybe 10 or 2 or 5, whatever it may be. Okay, I can go with 1 or I can go with 10, whatever it may be. So this is called as spacing. Grading, I told that here we are not going with any kind of an maybe the mesh is not that refined. We are not making the mesh, they are all uniform mesh. If I give something like 0.1, so what it is actually, 0.1 means from the surface where I am defining, so it used to be 0.1 at the exit, and from there every 10% it keeps adding. That's the meaning of it actually, grading actually. If I give 0.1, 0.01 like that. So to understand, to begin with actually, let's go with a uniform simple grading, that is 1, 1, 1. We'll keep it. Now, so coming to the boundaries, anyhow, edges, I'll keep it as it is because we are not using any curved surfaces. Maybe in the next example, I will try to show you how to define the curved surface. I'll show you how to, say for example, if I take your lid driven cavity problem itself. So I can have the bottom surface, I can have it as something like a curved surface instead of having a flat surface. I'll show you. Okay. Now coming to the boundary. So as I told that you have to name the boundary. So instead of inlet, I will call it as hot side. Okay, hot side, and your patch, the faces is once again 0, 3, 7, 4. The inlet I am trying to rename it. I am using the same thing. Then cold side. Okay. Hot side, cold side. Okay. The face is once again 1, 2, 6, 5. Now, remaining all the things I'm going to call it. So I'm not defining any wall and all here. Okay, I'm not defining any wall and all. I will just simply call it as symmetry faces. I'm not defining anything. So I'm going to remove everything and I'm going to call everything as symmetry. Okay, I'm going to call it as symmetry planes. It's no more walls. It is symmetry, and P should be capital LANES, symmetry planes. Okay, what it is actually, it's once again symmetry. What are the faces actually? 3, 2, 6, 7, 4, 5, 6, 7. Okay, 3, 2, 6, 7. That is what is there in the front. So if 0, 1, 2, 3, 4, 5, 6, 7. So it is 3, 2, 6, 7, 4, 5, 6, 7. Then you have 0, 1, 2, 3, 0, 1, 2, 3, then 0, 1, 5, 4. Okay, these are the 4 faces. Okay, let me define that. In the bracket, it is 0, 1, 2, 3. Then okay, just come over here. Okay. Then it is 0, 1, 5, 4, and close the bracket. So now all your vertices, boundaries, everything is defined. Okay, then you need no further thing. So everything is there. So this is your mesh file, block mesh dict file. Okay, this is your block mesh dict file. See, if you come to the header file and all, here you have the comments and all, which version of OpenFoam you are using, what you are using, what is the name. So this is the name. See, this is the name of the file. It's a dictionary, this thing, it's ASCII format. And there it's in the C++ language. Okay. Vertices, block, and your boundary. There are no edges and all. So once it is done, I'm going to save this. I'm going to save this and I will close it. Okay. Then I have to go to other folder. Which is the folder? 0 folder. Okay, I have to go to the 0 folder. I'll go to the 0 folder, flange, 0 folder. There you have your T file. Okay, I'll open this T file. Okay, so here you have the dimensions of it. It's a temperature. So interfield is a uniform 273. Then you have the boundary fields. You have to define the boundary fields. What are the boundary fields actually? So I defined it is hot side. Okay, it is hot, SIDE, capital SIDE. So it is hot side. So it is a fixed value. I'm going to give a fixed value. I will copy this. a fixed value, and I have to define the value. What is the value? Okay, so it is 370. So if it is 100 degrees, so I'm trying to define that problem. My hot side is at 100 degrees. Okay, instead of 273, I'll put 3 degrees, 373 degrees. Then your cold side. So I'm maintaining a delta T of 100 degrees. So your cold side boundary is actually COLD SIDE, cold side. Okay, cold side, it is fixed value with the 273 degrees. Then what I have actually, I have the symmetry. Okay, I have the symmetry. Okay, I have the symmetry. Let me define that. Okay. SY METRY PLANES, symmetry planes. So what type it is actually? It is symmetry with a no value, SY METRY. So I have defined the temperatures. I defined the temperatures. So this is what I have. I defined that means outside temperature, cold side temperature, and symmetry planes I have defined. So you can, once you are done, you can save this. Okay. Now go to the constant folder. Okay, you have transport properties there. You have transport properties. Just open this. Okay, you have this transport properties. Here, all the values you can see. You look at this is the epsilon actually. This is your transport properties. It's something like this. Property dimensions are. This is for kg, meters, second, kilo, mole, ACD. So this is how it is actually. So I'm going to go with only your mass and your seconds. So it is 2 and minus. So you don't do anything, but your value, that particular thing, whatever the value you have. So this particular thing, what type of fluid you are trying to use? What type of fluid you are using it? So if it is okay, this may be 1 into e to the power of minus 5 or 2 into e to the power of minus 5, whatever it may be, depending upon the type of the fluid. If you are using water or whether you are using your maybe air, whatever it may be. So if you are using air, I can go with either 1 e to the power of minus 5. Okay, I can change it. If I am using a higher denser fluid, I will change it to 4 into e to the power of minus 5. So here it is actually, this means that this is meter square per second. It's actually new value. It's actually the new value. That is your the nu by rho. So that's why this value is 1 e to the power of minus 5. So I defined that particular value also. Then I'm going to close it. So now I have to go to your system folder and open the control dict folder. Okay. Now in the control dict folder, okay. So what are the things I need to check actually in my control dict folder? So what is your start time? What is your end time? So end time, let it be some 100 or 200, whatever it may be. Let me see some 300. Okay. And for every write interval actually. So I want to write interval for every maybe 10 seconds or whatever it is. So if your delta t, if it is 0.1 or something. So I see what I am trying to do is a Laplacian form because I am trying to use a Laplace function. Okay. So your start time is 0 and your end time is so 300, or you can put 100 also. It may convert between that. So I am going to give some number 100 or 200. So delta t, so you can start with 0.1 or 0.2, whatever it may be. Let me start with 0.1. Okay. So then control this write interval time for every, because 0 to 300 I have given. So let this interval write for every 10 seconds. So 10 particular thing, whatever is there, is going to write actually. So write format is ASCII, all those things. It will remain as it is. Then, so to what precision you want, 10 to the power of minus 6, all those things remain same. And now you have saved it. Okay. Now come to CD. Okay, I have come to the flange. Okay, I've come to the flange. Now I can maybe I can run the block mesh. Okay, so now I got the mesh is generated. You want to check it means I have to type para FOAM parafoam. So flange dot OpenFoam, that is actually some kind of your parafoam, that output file is created, and your para will just open. Yeah. So just you have got this particular thing. Just click on this apply. Okay, you can see this particular thing. You can see this. See, this particular thing is run. This is what I have created. Okay. So you can, whatever the dimensions you want, you can zoom it and zoom out. So I have created a mesh. So what I'm going to do actually, now I'll go back. Okay, I'll close this particular parafoam. Okay, now I have to run it actually. So here I told that there are different types of solvers. I want to use for heat transfer, this is a heat transfer problem. I will be using a Laplacian form. Okay, LAPLACIAN FOAM, Laplacian form, and run the case. Yeah, you can see this. This is temperature. Maybe I stopped at some 250 iterations. So maybe if you want, you can give 500 iterations, whatever it may be. You can see that heat is flowing from hot side to cold side. And rotate this, you can see this. This is an hot this thing, and this is a cold thing. So just I'm trying to teach you the methodology. Yes, I've taken some very arbitrary dimensions I've taken, but to be very precise, I can give a particular dimension. So because last time we looked at that same 20 centimeters length, maybe we can take a smaller length also, maybe 10 centimeters. 10 centimeters of particular length, and you can solve it. So I'm trying to, this is a simple Laplace problem using your Laplace equation. That's it. Heat transfer equation. Only temperature control. That's it. Is that clear? Any doubts here actually? See, you have to work on the those files actually. See, here I am trying to create a mesh. From the mesh, then I am going to use the Laplace foam. That is the Laplace equation solver, and trying to plot the temperature. Okay. Now, shall we move forward? Hello?
Yes, sir.
Can you hear me?
Yes, sir.
Okay. So now, I told that we have cases where one of the surface may be curved one. Okay, one of the surfaces may be a curved one. So what I want to do actually, I will go to your what is called as maybe PITS daily, OpenFoam tutorials, incompressible, a simple foam. You had this what is that case? Icofoam, and we have a cavity problem here. Okay, so this cavity problem, I'm going to take this cavity problem, I'll take it out so that I can do some modifications. I will go to this a cavity problem. Okay, I'll show you what I'm going to do. So if I have a cavity problem, okay, I have a cavity problem, something like this. This is my cavity problem. This is a square cavity problem, what I have. Okay, this is a square cavity problem. What I'm going to do actually, I'm going to have a curve here. Okay, I'm going to have a curve, something like this. This is a curve actually. Okay, I'm going to have a curve. I'm going to have a curve like this. Draw this curve. Yeah, something like this. I have a curve like this. Okay, I have a curve here, and I have to get this curve. See, you have this particular thing. I have to define the vertices. So what I'm going to do actually, I will do the same this thing, but here I'm going to use the feature what is there in the black mesh, that is your arc feature I'm going to use. So now, say for example, I want to be in, so this is my x direction, and if I try to put it across something like this, y direction, okay, and you have your z direction. You have your XYZ direction. Okay, you have this XYZ direction. Now what I'm going to do actually, so if I try to name this, so this is my 0 vertices, okay, and this will be my vertices number 1, and this will be my vertices number 2. I'm going in anti-clockwise direction, and this will be my vertices number 3. So I have this vertices, so which was a square. Now if I make one of the thing as I'm taking only one surface, I can make a 3-dimensional if I have one more surface in the front, that is 4, 5, 6, 7, and I can define the same thing if I repeat the same thing. What I'm going to do actually, so what is the dimension here? So this is one unit, between 0 and 1 if it is 1 unit. So if I try to write this particular thing actually, so this is at a dimension, write the dimension. So the dimension is something like this. Okay, this is the midpoint I'm telling you. Midpoint at a distance of 0.5, and see this is my y direction. So this is positive y actually. So this is positive y. Let me define that. This is my positive y or z, whatever it may be. So my opposite, it should be negative. Okay. So what I will do, I will give some radius as 0.25 or something. So I just give minus 0.25. So I have given a center point somewhere, the arc. So what I want actually, I want an arc between the two vertices 0 and 1, and I am going to give this dimension x, y and z. So at any given, so how you are going to define the arc? So the arc can be defined in such a way that where I want an arc, I want it between 0 and 1 and the dimension. So this I can do in your blockmesh dict file. So what I'm going to do, if I do for the both the surfaces, I'll be getting the curved surface. Okay. Now what I will do actually, we'll go to this particular cavity problem. We'll take the same cavity problem. We'll see. We'll go to this particular. We have this cavity problem, and just we'll go here and we'll try to open it in the terminal. We'll try to open it in the terminal, and we'll go to that system folder. This is where we have the blockmesh dict. Okay, just I will go here, cd, okay, system, so gedit, okay, gedit system slash okay blockmesh dict. Now if you look at it actually, how it is actually, so it is 0 0 0 1 0 0 1 1 1 0 1 0 0 0 0.1. See, on the z direction I am trying to give 0.1. Okay, then in the particular z direction, same this thing. So one in the front face, one in the back face. One in the front face and the back face. I am trying to define all those things and all. Madam, badi madam class ತಗೊಂತಾ ಇದ್ದೀನಿ ಮೇಡಮ್. ಕೊಡ್ತೀನಿ ಮೇಡಮ್, ಮಾಡ್ತಾ ಇದ್ದೇನೆ ಮೇಡಮ್, ರಮೇಶ್ ಏನು ಮಾಡ್ತಾ ಇಲ್ಲ, ಬರ್ತೀನಿ ತಗೊಳ್ಳಿ ಮೇಡಮ್, ಬರ್ತೀನಿ. Okay, so this is your X mesh, this thing I have defined everything. So I have defined all the moving wall, fixed walls, and this is same as it is. So what I will do actually, I will just go to your, okay, I will go to your parafoam, and I will show you how that particular this thing will look like. Okay, if I apply, so this is the mesh right now. This is your mesh. If I go and look at the wireframe, this is my wireframe. This is surface which adjusts all those things. If I try to rotate all those things, this is my mesh. What it looks like now. Now what I want is actually, I want the bottom surface, one of the surface I want it to be the methodology I'm going to teach you. So one of the methodology, what I'm going to do actually, I want it to be made as an arc. So now, as I told, see how the numbering is there. So the numbering is behind surface, it's actually 0, 1, 2, 3. Front surface, it is actually 4, 5, 6, 7. Okay. So this is in X direction, this is in Y direction, this is in Z direction. X, Y and Z direction. What I will do here actually, I'll close this and I will go to gedit, same thing, and I'll open the blockmesh dict file. Rest all is there. Now I will utilize this edge feature. So just go there and plus enter. Okay, and plus tab. So now what is it actually? It is an arc. Okay, it is an arc. ARC. Okay, space. Where I want actually this, I want between 0 and 1 vertices. Okay, I am going to define the dimensions, that is 0.5. Okay, then minus 0.25, that is in minus Y direction, and 1 is 0, that is at that particular Z direction is 1, 0 actually. Then press enter. So same thing I want, this is a 3-dimensional thing. I want between 4 and 5. Okay, then the dimension is 0.5 minus 0.25, but in the Z direction it is 0.1. Close it. So now I have defined the arc. So instead of a square the surface, now this has become an arc surface. So this is how you can define the arc. Okay, this is how it has defined. I am defining the arc. Okay, that means that whole surface has become arc. So now I'm going to save this file and close it. Okay. Now what I'm going to do actually, I'm going to run the blockmesh dict. So blockmesh I'm going to run the blockmesh. It has run. Now I'll go to parafoam. See, it's opened, apply. See this? The surface has become, now we should try to look at the surface with the wireframe and look at this, what has happened. See this particular thing. Bottom surface, I have made it a curved one. Same thing I can do any surface. So methodology is what I am trying to do. So methodology is actually, I have to define the vertices, and in between where I want, say if this 0.1 or this particular, if you are able to do that, automatically that surface will take care and your curved surface is created. So I want to do the same thing in the top. So what I want actually, now it's between 0, 1, 2, 3. So I can give an arc between. So I will just go to this particular thing, go to my blockmesh dict file, okay, and just go and go to this blockmesh dict file. Look at this. I'm going to do something like at the top. Okay, I'll do the same thing. So both the surfaces I'm making arc. So what is the surface? 0, 1, 2, 3. Okay, this between 3 and 2. Okay, this is between 2 and 3. So instead of 0.5 minus 0.5, I'm giving it as plus 0.25. This also I'm making it. So this will be, see, 4, 5, 6, 7. Okay. So this will be 6 and 7. Sorry, it should be 3 and 2. 3 and 2. This should be 7 and 6. 7 and 6. So I'm going to save this close this, and I'm going to run the block mesh file. Let me close this and run your block mesh. So run the parafoam. Apply. Sorry, what has happened? It has come inside actually. 0.5 should have been in the other side, no? It should have been 0.5 plus 0.25. This should have been in this. No, it should have been 1.25. Sorry, 1.25. That should have been 1.25. This is 0.5. This is in y direction, 1.25. Block mesh just go there. Instead of 0.25, so this is 1, no? 1.25. Okay. So just I'm trying to teach you the methodology, that's it. Yeah, you can see this. Because this dimension was 1, no? So you should have given 1.25. So if you want, you can just check with the surface with the edges. You can see this particular. This is how you can use this particular arc feature to define this. So if you want a fine mesh, actually, you can just make it as finer as possible. Just go to the block mesh dict file. So if you open this block mesh dict file, you want a finer mesh actually. So just go to this particular thing. This 20 instead of 20, you make it 40. So x direction it will be 40. Y direction also it will be 40. Or you want 100, I can make it. So anything I want, this particular thing, I can do that. So see, in most of the other ANSYS, this thing and CFD and all, you don't know what you are trying to do. To begin with, actually, try to define the vertices, what I am trying to understand that. Ensure that your faces are not overlapping. Then try to create a, see, X mesh means it's a block mesh. Try to define the surface. Then you try to give the mesh, how fine you want a coarse mesh or fine mesh. Go with simple grading, 1, 1, 1 to begin with. Okay. Then how you want an arc surface is that, try to define the arc. Then the other boundary conditions you can define. Is that clear? Any doubts here? Yeah, you can unmute and speak.
No, sir.
Yeah. See, I'm taking very simple examples. See, even for your test also, CI also, I want to give simple tests, simple cases only. But try to understand, because you need little bit of practice for at least a week or so, you need little bit of practice. That's it, nothing else. Okay. Now, I told that we have a file what is called as a grading. We close this parafoam. Close this parafoam and okay. You have something called as grading. What is that? Yeah, this is a grading actually, which is 1, 1, 1. Now, what exactly this grading will do? So as I told us, grading means actually you are defining the grading in whatever the fashion, that is, maybe you want to get a uniform kind of a mesh. You want to get an uniform kind of a mesh. Now, I will try to play with this number 1, 1, 1 with something else, so that if I give a particular number, what will happen to your mesh actually. We'll see that. So what I will do actually, I will go here and edges. I'm going to remove this, any of this curve. I will make it this thing. There are no curved surfaces. So I will go with only your square system. Okay. I've come to this simple grading here. Look at this particular simple grading. So all this vertices, 8 vertices, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. So all these things remain same. The way you're going to define your X is also mesh. If you want to refine, maybe let me come back to the original number so that if people can see that. So 2021. Now, so what I'm going to do actually, now with this particular thing, So if I try to, already you have seen the mesh actually, what I'm going to get actually, I'm going to get a uniform mesh. An uniform mesh of equal size in X and Y direction. So now what I want is actually, I want to make, so let me show that actually, then that will be easy for you. Let me go to this particular thing, parafoam. Blockmesh, because I want to rerun it. Okay. Now this is what you have. Okay. This is what we have. Now what I want is, maybe in the Y direction, I want it to be 0.1 or 1. That means I want to have a refined mesh here or here. One of the surfaces should be refined. That means maybe you might have come across some kind of a boundary layer kind of a problem, where I want mesh to be refined at one surface and I want it to be coarse at the other end. Okay, if I want to do that, so let me go to this file. So I'll open this blockmesh.dict file. Okay, I'll go to this blockmesh.dict file. This, instead of 1, I'll make this 0.1 and I'm going to save it. Now what will happen, you'll see. Now I'm going to blockmesh, okay, then parafoam. Okay, now I'll apply this. So we'll come to the surface with it. Have you seen? So what has happened actually? It is 0.1, it is increasing in this particular direction. That's the meaning of it. Okay, so grading means actually this particular things at the top actually it has become 0.1. So slowly it is this particular in the direction, in this particular direction, there is an increment of 10%. That's the meaning of it. So there is an increment of 10% of your, so that's called as a refinement, which is required, what is required in your directions. Okay, now what I will do actually, I will come back here. I'll come back to your blockmesh.dict file. Okay, X direction I'll make it 0.1. Look at this. Okay. Save it. Okay. Then I'm going to blockmesh. I'm going to run the parafoam. Apply. Look at this. What has happened? So there is on the right hand side, it is 0.1. It is, that means I could see there is an increment. That is a refinement is happening in both your positive X and positive Y. Positive X and positive Y direction. So I want a refinement to the right hand side. I want it to be refined at the right hand side. So instead of grading 1, so I can see 0.1 I have done. So if you want, still you want finer, I can go with 0.01 or 0.0, or if you have a very large, huge volumes, I want it to be 0.01, I can go with 0.1. Okay. So now, is it possible to have maybe this refinement to the left hand side or right hand side, to the bottom and the top? Yes, it can be done. That means, so it has to be 0.1 here and 0.1 here. Okay, it has to be 0.1 here, it has to be 0.1 here. In between, I want a coarse mesh. It can be done. So that is also possible. So the refinement can be done at both the walls or both the surfaces. Both the surfaces you can have the refinement. That also can be done. So how it is done actually? So if I go back to this blockmesh, let me go to this blockmesh. Open this in your text editor. Okay, let me put back to 1. Okay, 1 already is there. Now to do this actually, so what I will do, I will take this, I will go to the This is how, if you want to do this, actually, you have to do little bit of modification. See, this is in which direction? X direction. If I will comment it, because this is the class, so this is in, I'm commenting it, this is for X direction. Okay, this is for Y direction. Okay, this is for Z direction. This is for Z direction. Okay, X, Y, and Z direction. Now I want this refinement only in that particular direction. So whatever the direction I want. Okay, what I will do, I will retain my, say I want the refinement in such a way that, so it has to be in a different, only in the Y direction I want some refinement. So what I will do, just I will keep X and Y as it, sorry, X and Z as it is. So for the Y direction, I'm going to make some modification. So here, so anything you want to do is actually, here just open the bracket, close the bracket. So what I will do, so let me give some 0.5, okay, some spacing of 10. So what is actually 50% of this particular thing I want in 10% value. Or I can go to the next thing, open the bracket, close the bracket. I can have 0.5. In the bracket it should come. You can keep 0.5, okay, 0.5 and 0.1. So what is actually 50% of my mesh? Actually it should be 0.1. So 10% grading, and the remaining I want it to be little bit coarse. So 50% of the geometry is of grading, that is geometry or the cell, is of 10, and remaining 50% is of 0.1. So that's just an optional number I given. You can give 0.2 also, you can give 0.01 also, just some arbitrary number I given. So what I'm going to do, I'm going to close this. I'll just go here and I have to close this parafoam. Okay, I will run this block mesh. Something like that. Something has happened. One. Did I close it properly? Close. Yeah, I think I have to put a bracket. Yes, I forgot to put a bracket. I deleted, no, that bracket. Yes, 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 yes. Bracket open, bracket close. Yes. Now it will has to work. That's why, say in OpenFoam, if you make this simple errors, this will come. Now it's worked. Okay. So parafoam. It comes with some practice. That's it. So nothing. I'm not doing any great thing. Only things you have to do a little bit of practice. Now you see. So 50% of this particular thing is in the 10. Maybe it's a coarse mesh. 10 you can give 10, 15, or doesn't matter. So remaining 50% is of 0.1%. So this is how the grading. So this is how you are. If I can do the same thing for X direction also. I can do the same thing for Y direction. I have done for Y direction. You can do the same thing for X and Z direction also. So this is very much important when you are doing some kind of a pipe flow, where you want a coarse, maybe a very refined mesh at the walls, and you want a coarse mesh at the center of the pipe. So this kind of methodology will work. Okay, so that can be done easily done using your this particular thing, what is called as this particular grading. Even though name they have got a simple grading, so simple grading, it is actually by default this will be 1, 1, 1. By default this will be 1, 1, 1. Or I can see some of the books actually I've seen OpenFoam tutorials, they go with 1, 2, 2. Okay, 1, 3, 3 also. So that also can be done. So they're all methodology of grading. That means I want 1 in X direction, twice in Y direction, twice in Z direction. That's the meaning of it. There's nothing else actually. Okay, there's nothing great in that actually. So if you want, you can, instead of 10, I can put 15 also. 15, and I can run. Paraform, you close it. Okay. Block mesh, paraform. Yeah, just flow here, apply, and you can see. So that will come. If you go with whatever the number, that is taken care depending upon the dimensions. Okay. Now, this is about your how the grading will work. The grading will work. See, what we have seen is actually they're all single blocks. They're all single blocks. So in your OpenFoam, we can do multi-blocking also. So multi-block meshing also can be done. Okay. Delete all those things. What is this multi-blocking? Is that clear? Any doubts here? Hello? The same. Others? Hello?
Yes, sir.
Can you hear me? Any doubts here? The only thing is you have to practice it a bit. Whatever I told, no, just take the cavity problem and you practice. Okay. Now, I'll tell you what I mean by this, what is called as multi-blocking. So you have a surface something like this. Okay. You have one more surface, something like this, which will be coming like this, or this is how it is. Okay. Okay, you have some kind of a T section or I section, whatever it may be. T section or I section. So now, so if I go with, if I want to block this particular, if I want to mesh this is some block 1, okay, and this is your block 2. This is your block 2. I have 2 blocks, a T block. So this kind of mesh can be done in 2 ways. This kind of mesh can be done in 2 ways. One is, see, the second block can be divided into 3 blocks here, 3 blocks, and join with the block number 1. Join with the block number 1. Or I can define the first block, I can define the second block. Okay, so 2 ways I can do. So in that case, if I go to divide this block 2 into 3 smaller blocks, actually in that case, I'll be having 4 smaller blocks. Either you can go with 2 blocks or I can go with 4 blocks. So you can't tell which is advantageous, which is disadvantage, because you will end up with a similar kind of mesh strategy. Doesn't matter whether I'm. But what is important here is actually this particular junction is there. No, that junction should able to transfer the energy or properties. That you have to take care. If you're able to do that particular talking to each other, then your meshing is fine. If you don't do that actually, then your meshing will be failing. That means what will happen? You have a wall. Say I'm trying to do some kind of a problem, fluid flow problem. So the fluid is not interacting, the fluid which is coming from one. Say I have an inlet here. It has 1 inlet and 2 exits. The fluid coming from one will not talk to this wall, and it won't, you see, there is some discontinuity in the boundary. There will be this simple discontinuity in the boundary. So that discontinuity you can break it only if you're able to give this junction with a proper boundary condition. that fine?
Yes, sir.
Okay. Yeah, we'll try to stop here. So I have to go to CAD lab and I'll try to see that this installed.